Hello and welcome back to Differential Equations on this glorious Tuesday at the end of the month of, February, I guess. We're going to continue talking about non-homogeneous equation, the undetermined coefficients, and variation of parameters. So we said that we are going to have a complementary solution, which we get when we solve the homogeneous part of the equation, and then we're going to have a particular solution added to it, which is obtained either through method of undetermined coefficients or a variation of parameters. So we're going to first review, since we had to stop last time due to impending doom of the exam. We are going to now do one problem for undetermined coefficients, then switch to the variation of parameters, and then go to the next section where we do word problems and some useful stuff. So what are we doing now for this? Let's see. Looking for a problem. So let's take a look at problem 39 because we can. The third derivative of y plus y double prime is equal to x plus e to the negative x, and we have y of 0 is equal to 1, y prime of 0 is equal to 0, and y double prime of 0 is equal to 1. So these are our initial conditions. So we start with complementary solution first. We are going to solve y to the third derivative plus y to the second derivative equal to 0. Characteristic equation immediately. And we are going to look at these r's here and say that's going to factor out r squared, and we get r plus 1 as a leftover. So we have r squared equals 0 and r equals to negative 1. So we have r equals 0, multiplicity 2, and we have r equals negative 1. So what are the solutions look like for this one? Anyone? We have e to the negative x, but then what? What else? So we have yc is equal to c1 e to the 0x plus c2x, it's duplication, e to the 0x plus c3 e to the negative x. Are we all okay with this? Now how much is e to the 0x? 1. So yc is equal to c1 plus c2x plus c3e minus x. That's a complementary part. Do we all get this? But this could have easily been the previous exam, right? This question. It wasn't, but it could have been. So now the next part is to deal with the x plus e to the negative x. So now we're talking about particular solution. We have that f of x is equal to, what did I say? X plus e to the minus x. X plus e to the minus x, then the first derivative would be 1 plus e to the minus x with the negative here. Then f double prime of x is going to be 0. Minus and minus give me plus, so it's just going to be e to the negative x. Third derivative of x is going to be negative e to the negative x. And then from that point on, it's going to oscillate. So now, when you put all of these together, what do you get? Anyone? Don't we get ax plus b plus c e to the minus x? Do you guys see that? We have a constant term. Well, first of all, we have x here. So that's linear term. That's ax. And then this is 1 and then zeros here, right? 0 plus this and 0 minus that. So when over here also I have 0 for constant term. 0, 1, 0, 0. Right, so that changes. So that's b part. And then you have positive e to the negative x, negative e to the negative, positive e to the negative x, negative e, right? So that's 1, negative 1, 1, negative 1. So that coefficient flips around. That's c e to the minus x. So when you look at this, all types of function are now featured in that part there. But now we have issues because all of these, duplicate what we already have. You see, b is duplicating c1, ax duplicating c2x, and c to the minus x duplicating this. It's just they're not called C1, C2, C3, they're called ABC, but they all duplicate that. Now what do we do for duplication? For duplications, we have to multiply them with either x or ln x to make them linearly independent. So that gets ln x, that gets ln x, that gets x. And then they become linearly independent. And I'm not sure if the book is explaining that well at all, because I don't see them actually having anywhere explicitly said these are the things you multiply with in order to make the linear independent solutions. So I'll write here in blood, all three are repeats. Because all three are repeats, we are going to use the trick. So I'll start with B first. I could have started with B. You know what? I want to change it because I can. A plus bx plus c. There. That's better. So we have a constants matching and so on. So A ln x plus bx ln x plus cx e to the negative x. Now we know what to do. Differentiate it 3 times, plug in equation, and work on those coefficients. So we need to differentiate this 3 times. This is where all the fun begins. Now we have the product rule here. So that's going to be copy the first times derivative of the second plus copy the second times derivative of the first, which is just b, plus another product rule, copy the first times derivative of the second. So that's going to be -1 e to the negative x, plus copy the second derivative, this is c. So e to the minus x divided by c. Is this good for the first derivative? Is anyone following this? The derivative of an x is 1 over x, and I have a. This is the copy the first one as is, take the derivative of the second, which is 1 over x, plus copy the second derivative of dx is just d. Dx over here, copy the first, which is cx. Derivative of this is negative in the chain rule, so that plus e to the minus x. Why do I have divided by c? The product rule, copy the first. Yeah, it's time to see. I did this just to see if you guys pay attention. That time will work. See. Cool. So these guys will cancel. Well, now we need the second derivative, and then eventually we'll need the third one. I know, it's brilliant. So this is going to be -a over x squared when I take a derivative, plus 0 because derivative of b is 0, plus derivative of b ln x. What's the derivative of ln x? Great, so plus b over x. Plus, hey, we have the product rule again, maybe minus. Right, we have the -1 go in front. So now we have the product rule again. The product rule will say copy the first one, which is cx, times derivative of the second, which is -1 e to the negative x, plus copy the second, which is e to the negative x, and then times c, so c e to the negative x. Awesome. Plus the derivative here is -1 c e to the negative x.
With the -1 change, could you put the derivative of -1 e to the negative x? With the derivative of that, negative cancel.
You're talking about this one?
Yeah.
I took that negative here.
Oh, okay.
The answer to your question would be yes.
Okay.
Yeah, so I took that -1 out, so now I have to distribute everything and to make it look pretty as much as I can, because we got to take one more derivative, huh? Yay! So -a over x squared plus b over x plus, because minus and minus, cx e to the minus x minus ce minus x minus ce minus cx. Well, that combines into 2. All we need to do is plug all of. Oh no, we need one more. Yeah. Let's not get excited, or as we say, ahead of ourselves. Let's get right with ourselves without getting ahead of ourselves. Can anyone just tell me what this is? So we have -2, +2, so 2a over x cubed minus, there will be -1 so negative b over x squared plus product rules get me now. Copy the first times derivative of the second plus copy the second times derivative of the first. That's this one. Minus will give us plus. So 2 c e negative x. So when you're looking at this, if you say, well, what happens between two lines? Well, obviously minus changes to plus. But the derivative of e to the x is e to the x, derivative of negative e to the x is -1 e to the negative x. So that's -1 changes minus the plus. Great. What now? Now what? Exactly, simplify. Very good. So the pen stops working, obviously, at the worst of times. I wish these pens were like the new ones when you can just click to do this.
Wait, what?
New pens. You don't, it's not as, right, you can just twist a little bit to the side and pop it open. Yeah. I have to do this for like 15 minutes. New pens are much better. What happened? Yeah. 2a over x cubed minus b over x squared minus cx, I forgot e over here, e to the negative x plus c e to the x plus 2c e negative x. These are like terms, right? I hope this is the last time I'm writing it. All right, so I have the second derivative over here, and I have the third derivative over here. So those are the two that we need. We have to plug those in the original equation where they belong. So third derivative there, second derivative here. Actually, sorry. Here and here. And then you have to, like you say, just do it. All right, so plug it in and get that while it's still young. If you don't know what the differential equation is, it's y to the third derivative plus y to the second derivative is equal to something. X plus e to the negative x. So now you have the left-hand side in terms of a, b, c. Plug in this entire expression, right, for the third derivative. And the one for the second, you just grind to algebra. I'm back in about 30 minutes. By the time you're done with this.
Would you come to school this? Formula sheet, would you come out?
Okay.
You put the matrix, matrix on? You guys are like matrix.
Oh yeah, this is for the like nodal analysis.
Yeah.
I don't know. That was kind of weird.
He doesn't use stuff that you just don't know what it is, but
Yeah, it was just the same.
it's so weird, man. Your picture is so
So Family Girl was on with her passes and sort of like that. I don't remember how to do that.
I don't think we're gonna have to do it. Just have to write that. That's all it. Maybe we'll just solve for like 100%.
Yeah, that's the only time I think it's actually like quicker. Well, not even quicker, but you're just looking for like one part, not like clear all the time.
Especially like live.
Yeah, did you print out the line and see that? I was looking for the book last night. I'm not seeing this thing. It's already like,
What's the free that you have the Amazon?
yeah. I'm not gonna do it until during last.
You take cameras professional.
Yeah, and two, I took it out.
Oh, yeah, you're right. Yeah, right. You like crazy, it's crazy to do that.
Oh my god. Hated it, like, I did chemistry.
It's a grind, right? It's a very large grind. You plug everything in. Two a x cubed minus b over x squared minus cx e minus x plus 3ce minus x, and then we have minus ax squared minus a over x squared plus b over x plus cx e to the negative x minus 2ce negative x equal to x plus e to the, so minus 2ce minus x equal to x plus e to the minus x. There we go. Awesome. So I have this term over x, so 2a equals 0. Then I have these two terms, which is minus a minus b equals to also 0. Then I have this term that it's also 0. And then I have negative cx. These two terms cancel completely, right? And these two terms make a ce to the minus x. So that is equal to 1. So c is equal to 1. So a equals 0, b equals 0, c equals to 1. And I have those here. So both ln terms die, and I'm just left with x e to the minus x. So the general solution is the complementary solution plus the particular solution. Complementary solution 5 pages ago was C1 plus C2. So C1 plus C2x plus C3e to the minus x, I hope. Yep. And from the yp, only the last term, so that will be called C4. So only that one survives. Oh no, it's 1. So that's particular solution, sorry. So it's 1, so plus x e to the minus x. Now we're almost done because we have 3 initial conditions, right? We have to plug into this. So we have to differentiate this twice. So I'm going to box this and say general solution. And then we're going to differentiate and do whatever we have to for those initial conditions. So this is the y prime. First one dies, C2 plus, no, minus C3e to the negative x plus the product rule, which is x negative 1 e to the minus x plus e to the negative x. So that's the second one. And now the second derivative, that dies. We have C3e to the minus x. That's a negative 1 there, so that's a minus. Another product rule goes here, and then we just have minus e to the minus x at the end. The product rule here is, I took minus 1 out, so it's just going to be copy the first times derivative of the second plus copy the second times derivative of the first, which is just 1. Awesome. So what's y double prime in the end when the dust settles? It is minus and minus give me plus x e to the minus x minus e to the minus x and then minus e to the minus x, which makes 2 of those guys. I'm just going to erase this. Awesome. Now we have those initial conditions that are also somewhere in the problem. There they are. So condition y of 0 is 1. We utilize the general equation that is boxed. So all x's are zeros, and it's equal to 1. So 1 is equal to C1 dies, no, C1 remains, C2 dies because x is 0, C3 remains, and the last term dies because x is 0. So that's the first one. The second one is the first derivative. 0 equals, because the condition is equal to 0, C2 survives, minus C3 survives as well, and then this one dies because of the x, and that's when it's plus 1, right? Because e to the negative x, which is e to the 0, is plus 1. Okay? And the last one is also equal to 1, so 1 equals. Maybe I should be writing these. So now for the second derivative, when I plug in 0, it's just going to be C3. And then that's 0. And then that's minus 2, right? So from here, we know that the C3 immediately is 3. And because C3 is 3, C1 from the first equation must be 1 minus 3, which is negative 2. And now I have C2, which is C3 minus 1, from the second equation, C2 is C3 minus 1, so positive 2. Nice. So we can finally write the particular solution, the full particular solution, and that's C1, which is negative 2, plus C2, which is 2, is that 2x? And then C3 is C3 is 3, so plus 3 e to the negative x, and then plus x e to the negative x. Is it like 2 pages? Easy? Yeah, easy, right? Welcome to undetermined coefficients. All right. So method of undetermined coefficients is you first solve the homogeneous case by using characteristic equation. Once you're done with that, you make all of the linear combinations of derivatives that you can, and then find those coefficients that determine coefficients. There you go. Determine coefficients by plugging in derivatives in the original ODE, and that's it. So what happens if this method fails? What happens when you can't use undetermined coefficients because the list of derivatives that you are taking is not finite? You know very well that when you take derivative of sine, it just alternates between sine and cosine. Even if you have product rules like e to the x times sine x, that's also going to loop through 4 combinations. But what's going to happen when you have a function whose derivative you take and it never stops changing? You know that polynomial is eventually going to hit the 0, and then it's going to be 0 always, and always after that. So yeah, you might have to have 5 terms, right? If it's 4-order polynomial, but eventually it dies. Eventually it dies. What are you going to do if there is more, not complicated function, but more menacing function in the sense that you start taking derivatives and it doesn't settle down to any repetitions, like tangent x. What's the derivative of tangent x? Right? Secant squared. And then what's the now derivative of secant squared? It's 2 secant to the first times the derivative of the secant. Now what is the derivative? It's a secant tangent, right? So you see how, as you now, and then you run into a product rule. This thing's gonna explode. Same thing, start with ln x. Like what do you do with ln x? 1 over x, and then negative 1 over x squared, and then, right? Now that one is never gonna go to 0, that one is gonna keep growing powers in the denominator, right? That one never settles. So you can have functions that will not exhibit this behavior where you can, just by taking few derivatives, kind of get into either situation that oscillates between few forms or ends up with 0. Because over here was easy, right? Polynomial, constant, 0, 0, 0, 0 forever, and then e to the negative x plus the sign in between. It's easy to come up with a form. I know that this is an issue because it was a repeat. That's a separate issue, but the whole method of undetermined coefficients hinges on this ability to just be able to find the pattern, and then that pattern has finite amount of terms, and then you just grind through them. So what do we do when we run into a tangent? What do we do when we run into ln? What do we do when you run into, I don't know, secant or cosecant or some other functions? Well, in that case, we are going to use this method of variation of parameters. Now, method of variation of parameters has a fairly long derivation in the book. Those of you interested in mathematics will obviously look that up. And what I'm going to do is I'm going to write the formula that I'm not going to ask you to memorize this because really formula is awesome. Those of you who did class preps, as you can see, by the way, those watching on the stream, there is a whole pile of class preps on the desk, about 17 for all 3 students that are in class right now. All right, so let's take a look at variation of parameters. Where do we start? Well, we have our good old y double prime plus p of x y prime plus q of x y is equal to some force function f of x. Your solution is going to be yc of x plus yp of x, so the same in terms of you are adding complementary to your particular solution. But now, and yc, this is just constant coefficient, so we know how to get that. This is the evil part right here. So what is the formula for yp of x? So negative y1 of x integral of y2 of x times f of x divided by the Wronskian of x. Oh, it's just not a big deal. Plus y2 of x integral of y1 of x times f of x divided by the Wronskian of x dx. There we go, simple. That's all it is, just this. So negative y1 and use y2, and then positive y2 use y1. What do you mean Wronski? Well, you're going to get complementary solutions. So this y1 and y2 are from the complementary solution. So y complementary is c1y1 plus c2y2, and those are your y1 and y2 that you're getting. Should we do an example of this, or you got this? Everyone wants to see some integration. See me in my natural habitat. Exactly. How are your hyperbolic functions? Excellent. Just toss that in there. Y double prime minus 4y is equal to sine hyperbolic of 2x. See? Beautiful example. Absolutely beautiful example. So we have our y complementary first calculation, and that calculation deals with the characteristic equation r squared minus 4 equals to 0. So we see that r is immediately plus minus 2, which gives us the complementary solution yc of x to be c1e to the negative 2x plus c2e to the positive 2x. And I'm just going to say hello y1 and y2. They have to be obviously linearly independent. So now in order for us to construct the yp, I have to create a Wronskian with these, work out the Wronskian because that also goes into the mix, and then just plug everything in and then just integrate and be done. So let's go create the Wronskian. So now we're working on the yp part, and the way we do this is we create the Wronskian first. So we have e to the negative 2x, e to the 2x, then the derivative of this, negative 2e to the negative 2x, and then 2e to the 2x. When we have these guys multiply, e to the negative 2x, e to the positive 2x, we get e to the 0, so there's just 2. Minus, and minus will give us plus, this is going to give us another 2, and the Wronskian is 4. Ah, beautiful. We got the Wronskian. It's just a number. So now I should be able to put yp together. We said negative y1, which is e to the negative 2x, and then we have integral of e to the 2x times sine hyperbolic 2x divided by Wronskian, which is 4, and then dx, plus y2, which is e to the x, times the integral of y1, which is e to the minus 2x, times sine hyperbolic 2x divided by 4. Do we integrate sine hyperbolic here? So this is why you need to see this in class so you don't get ideas. What I've seen once is the student take this, put it inside. I said, no! Because that would kill this, right? Because, you know, this exponent and this exponent here, they work together, and hell no. Can't move across the state lines, okay? Which is the integral. Nope. We write the sign out, multiply by e to dx is going to kill one of the e's. So this is e to the negative 2x, and then in this integral it's e to the 2x times e to the 2x minus e to the minus 2x over 8, because this gets over 2 dx, plus e to the 2x integral, e to the minus 2x, another sign hyperbolic here, so e to the 2x minus e to the minus 2x dx divided by 8 again. So now when you distribute this, you see that the second term dies, and you're only left with e to the 4x over 8. So we can kick out over 8. We can outsource it. and you are left with the integral of e to the 4x dx plus ship 1/8 outside again, so it's e to the 2x over 8. When you multiply, the first term dies, and then that's a negative there. That's going to be a negative here of integral of e to the 4x dx. So you see how easy this actually is when, you know, everything falls in place. So negative e, negative 2x over 8. The integral of this is going to be e to the 4x divided by 4. Anyone? No one cares? Whatever. Minus e to the 2x over 8. And we have another e to the 4x over 4. And we have plus c eventually. It's only working on the yp. Now imagine the limits after this. The initial condition. So now when you multiply this, you get negative e to 2x over 32 minus e to the 6x over 32 plus c. That's your yp. So all we need to do now is to put the solutions together. And I'm hoping for no repeats. And I do have a repeat. So y of x is yc plus yp. What was yc? C1 e to the negative 2x plus C2 e to the 2x. And now here's the issue, we have a repeat here. So minus x e to the 2x over 32 minus, and this one is not a repeat of anything, so we just have it as is. Let me put this answer on a cloud for you. So you see in the formula, you know the formula, you just plug stuff in and you are done. So yp of x is negative y1 of x integral y2 of x times f of x divided by Wronskian of x, sometimes that's a function, not always a number, dx plus y2 of x, the integral of y1 of x, f of x divided by w of x dx. I know the formula because I learned it by saying, okay, first solution first, you put the other one there, and the second solution, put the first one there. They're both divided, multiplied, and by f of x and divided by Wronskian. So it's not that bad to memorize it, but then you have another 5,000 things to memorize. And that's 2.5. We'll take a short break and then word problems. Forced oscillations and resonance.